Do you know, by the way, do you know manga, the Japanese comics? There is a very nice Japanese comics on the game of Go. If you are interested in the game of Go, you really have to look at this. It's called Hikaru no Go. I don't know if there is the original title, but yeah. And well, it's the story of this small kid which has a kind of ghost that teach him Go from the far past, and it's nice, very nice comic. But talking about the game of Go is originated from China, but became very popular and famous in Japan, especially during the Edo period. So after 1600 and later, and then now, of course, now it's probably more popular in Korea and China than in Japan. But it's still very popular. And let's see. For the general public, Go, this is an actual Go play, became very, on the news, very famous because for the first time, a computer beat the human champion. And if you remember, the first time that a computer beat the human champion in chess has been like 20 years ago. And nobody really thought that any computer could beat a human at Go for another 20 years. But then Google came out with this new approach of deep learning that allowed that. But this is just to give you the idea how much more complex Go is comparing to chess. Chess is quite easy to manage from a computer point of view. Go is on really, really hard. But we won't talk about deep learning. That probably will be a future talk. We'll try to stay simple here. And just 2 words about the game of Go. So the game of Go main, this is the board where professional player play, or when you know the rules. But you can also play with a smaller board if you are learning or if you don't have much time. And the nice thing is that all the pieces are the same, and it's very easy. And we have this combination that seems, if you don't know Go, this seems really like random. People put in pebbles on the table. But it's an incredibly complicated position that has a lot of subtle fight that is going on. So if you have time, I really encourage you to learn Go. It's a very nice game. But let's see. Just a word about after Google won beat the world champion. Another team in Google did something even better. They programmed a Go computer, a Go program, to play Go without looking at any game. The first generation of AlphaGo basically took all the game from a big champion, human champion, and analyzed them, and they came out with their UI. But then Google did this AlphaZero, which is a version of the artificial intelligence, of deep learning, that started from scratch, from zero. So just playing against itself. And this graph, basically, this one, you can see that it started, this is kind of a Go ranking. It started very, very low, like not even a beginner is so low. But then it started going up and up and up, and then this is more like a human champion, and this is the world champion, and this keeping up and up and still improving. And at some point, Google just stop the program, because to do this kind of simulation, you need 1,000 machines running in parallel. So it's quite expensive also for Google. It's not something that you can easily do on your own. And in case you are interested in computer Go, the first one is a client. So basically, any Go program can use that client. There are some protocols. And then there is this kind of 3 generation of Go software. The first one is a new Go, just open source software. The first generation is using a kind of rules, like in chess, to analyze the position, and it's very weak. I mean, I can even beat it. It's really weak. Then the second generation came out with something called Monte Carlo tree search algorithm. How many of you know about Monte Carlo tree search? Just heard. We will look at it later because that's implemented and it's quite interesting. And then it's probably able to beat any non-professional player. And then there is the AlphaGo one. But they did also a clone in open source, which is called Lila Zero. And the interesting thing is that being open source, of course, they cannot rent thousands of machines for years, for months. So what's happening is that anybody with a good GPU card can download the program, run in the program, and then give back the result. And then they keep a result from all the people together. And it's already the strongest open source software for Go. It's already able to play at like a professional level, human professional level. Not beat the human champion, but completely beyond my level or any non-professional player. This is my take. Of course, this is the GitHub repository. I just started at the beginning of this year, and I like because it's small. It's a few hundred lines of code. If we exclude the test, it's quite easy to understand. The code is, I think, quite readable, and of course, it's not incredibly optimized. But all the other program that we saw is written in C++, so it's quite hard to touch or to change. And it's able already to kind of have a nice game. And in the future, I plan also to put deep learning support, but for the moment. By the way, this is my Twitter handle, Ramtop, if you like this talk, if you wanted to discuss further, or you don't have some question, you can also ask me on Twitter later. And basically, this is the book. Now I think it's finished. It's not me anyway. And basically, I took a kind of inspiration of their Python code, but I wanted to be in Kotlin, which is much faster. And then, but just some ideas. If you are interested, also this is a very good book. Okay, these are a few lessons that I learned writing this software that I'll show you. Kotlin is a very nice language. There is functional programming is also a very good pattern for this kind of high performance. The other stuff, maybe if you don't know Kotlin, you cannot really, I show you the code to make it clear. But also another important thing is that people are thinking usual that to make something goes faster, you need to save CPU cycles. So when you look at an algorithm, you try to figure out where CPU is doing more work and try to reduce them. But on the modern program, memory is much more important than CPU. There are many cases where putting more CPU, putting something that seems slower, but it actually saves memory, either because it saves going to the main memory just using the local cache, or because it produces less garbage for the garbage collector. It's locate less memory. This is much more constraint in the modern JVM languages. And you can have a much bigger improvement optimizing the memory usage than optimizing the CPU cycles, which the Java compiler is very good at optimizing CPU cycle. Okay, so let's go back to the game. And so these are the rules. Very simple, black and white. So each one has one stone color, I mean, and then you have a lot of stones. The stones, you place the stones on the board, and you never remove, or you cannot move, basically, the stones. You can only remove the stone if you completely surround them. So, for example, black, when I play here, it can get the 2 white, or even here, I get the 2 right, or here, I can get the 2 white. And so you kind of understand that just from this, that it's easier to get stones, these are called stones, on the corner or on the border, rather than in the middle. You need more stones to surround. It's harder. So usually the first strategy in Go is first to get the corner, then get the border, and then the fight for the center. Of course, if you are a professional, there are much more, but for beginners, these are the main rules. And there is incredibly, so you need to completely surround, meaning that there must be no spaces. So white are not dead yet, but if black put the one in the middle, it can get all the white. So they are technically dead, because there is nothing that white can do. It cannot suicide, or so this is a position that is already secure for black. But in the second case, white cannot put a stone in one of the red position. Is that clear? Because in either of them, white will be kind of a suicide, because you put a stone completely surrounded, so you cannot put the stones. But since if you can put the 2 stones at one time, you can get the black ones. But since you cannot play 2 stones in one time, black is unconditionally alive. There is no way for white to kill that black position. So, and this is let's see the third. These are called I. So if you have a 2 I in your group, you are alive. But there is also called false I, like in that case, A is actually killable. So if white play on B and C, then black cannot do anything, because if black put a stone in A, then white can kill using the other I, or otherwise white can play on A and get the 3 black stones, and then the rest is just 1 I, so it's dead. And the interesting thing is that there is no rules that say with the 2 I's you are alive, but it's just a kind of a consequence of the basic rules. So the whole point of Go is trying to have a position with the 2 I's and try to avoid the 2 or more I's, of course, and try to avoid the opponent to develop such a position. And then, of course, the one that surrounds more territory win at the end. And this is, the capture, which I told you, but if you write an algorithm for that, is a bit tricky. It's not something that came out in 5 minutes. And so we define some words to help us. So a stone is a single piece. A string is a set of stones which are in contact. So in this case, these 3 are a string, this is a string, the black is a string, but this and these are 2 different strings because they don't touch. Diagonal doesn't count. And then we have something called liberties, which are the place which are not occupied by stone. So in this case, for example, the black group, the black string with the red dots has two liberties, the one called I and the square one. And liberties are more important, very important, because there is always a liberty race. Kill the liberties of your opponent until you have some liberty, because the first one die, basically. And in this position, the first that play can win. But if you don't, I mean, you have to think a bit about it. But yeah, it's quite also the kind of problems are quite interesting. And this is the code. So I don't pretend that you can read, just. But the kind of interesting thing is that this is Python code, and this is Kotlin code. And I translated, this is Python code from the book. So my first things was to take the code from the book, translating in Kotlin, and then I started optimizing Kotlin. So the current code of the book is a bit different because it's more optimized. But you can see how Kotlin is very, very similar to Python. I mean, as a syntax and also as a number of lines of code. If this was done in Java, will be at least double the lines of code. That's one of the Kotlin selling points. We are much more productive in Kotlin. I mean, I don't have any shell or JetBrains on anything, but I really love Kotlin because allow me to be completely type safe. And I mean, having both the advantage of Java, like in type safing, and in Python as expressivity, fewer line of code. I also like Python as a language, but yeah, it's. And then on top of Kotlin, there is something called functional programming that you may heard of in these days, and Kotlin is very good at functional programming, which is also something that is coming to Java. I mean, we have a Lambda in Java. We have streams. In the future, we have value types and something similar. But in Kotlin, you already have this today. And this is something called basically algebraic data type. How many of you know what algebraic data type is? Or the concept? Perfect. So maybe. So the idea of algebraic data type is that you define a type, in this case move, and then you say that this type is can be this, this, and this. You kind of define the type as a sum of different other types. And because this is this is a function, so this is just the way of Kotlin to define a function. But this data class for Kotlin means that is just a class with one field that point, and then Kotlin implements, I mean, usual like equal, hash, to string, all the usual method that you do if you have like a kind of value type in Java, and also is immutable. So that means that move can be a play, so something that plays somewhere, a pointer somewhere in the board. Another kind of move is a pass, that when someone passes, so there is nothing, no other information. Or another kind of move can be assigned. And now the nice thing is that we don't have to, for example, this code in Python is like the move. You have the point, then there is a flag is pass, or is another flag boolean is resign, because of course you need to know which is. But in this way you can keep the three concerns completely separated and just say move can be one of these three, and then the compiler will sort it out for you. And when you're using this, basically you have a when, which is a kind of a switch. And then you say, in one case, two case, three case. And in that third case, you can use the internal field of the. And this is also something that is coming to Java. Maybe not Java 12, but Java 13 or 14 for sure. It will have this stuff. Instead of when it's a switch, but they are actually working to have this kind of stuff in Java. But in Kotlin, we already have. So it's quite nice. And one typical thing is that, for example, we have here a node, a tree, and each node needs to keep track of the parent. But which is the parent of the root node? Usually you put like a null or something like that. But in that case, you have to keep, if the parent is null, you have to, every time you call parent, you have to put if is not null, whatever. Instead, in this case, you can just say, we have an algebraic data type, which is the tree, the Monte Carlo tree search. It can be a root or can be an actual node. And then you just put the parent of the root is a root. And that's it. So you don't have to worry about checking for null in your code. Which is nice, I mean. Do you agree it's nice? Makes sense? Okay. If you have any question, technical question, stop me. And go back to the game. A tricky part of Go is to understand who wins, which is something that in chess you really don't have this problem. Because if you have a position like this is a small board. The goal is to surround more territory as possible. So you can see that the position is more or less, A is more or less equal to B. F is in the middle, so nobody can use F. So it's kind of, it's called dame, but it's kind of territory that nobody can use. And you can see that C is unconditional alive. So those 2 points in C are already black territory, no question about it. But then you can see that D is similar to C, but it's different because the cornerstone is black. And this means that even if these two seems kind to be whitish territory, actually D is dead because black can kill D as much as you want. So all these D position stones are actually black. So in this case, black is win. But if you're human, you need to know the rules. If you are a computer, it's not so easy to understand that which is dead, which is not dead. Because when you play between humans, you know the rules and you can easily say this is dead, so let's count. Or if they don't agree, if it's dead or not, you can keep playing until someone wins. But the computer is quite harder to say which is not dead and which is not. So what computer does is he keeps playing, basically. If you ask him is it alive or not, he keeps playing to see until the end. When you already have a position like that one, where there are only 1 point holes, basically, then okay, there is no more sensible move, and then you can just count the position. And okay, already middle of the talk, I wanted to show you some code. But this is just to give you some example. The Python on a small board, the Python code was taking about 10 milliseconds for move. After a few improvements, now it's taking more or less 1/4 of a millisecond. It's also interesting that using immutable structure, instead this idea of strings, using immutable rather than mutable, really did a big improvements, because Java compiler is able to figure out when something is immutable, can use more aggressively optimization. And then, okay, this is enable mark. Instead of compiling every time, I'm caching some, which is kind of a usual strategy. This is an improvement on the algorithm, which is also kind of CPU level. And also this one. And this is also an improvement on the algorithm. But for example, the last one is, which is still significant, is using array instead of a map. We, as a Java programmer, we use a lot of map. We tend to use, but if we have a performance problem, map is quite bad. It's a very big class, which is very difficult for the compiler to optimize, because Java compiler is especially good at optimize a very small method. Instead, Java has very long, map has very long method with a lot of shared memory. It's very hard for the compiler to optimize. And in some cases, for example, we use a map just because we are lazy. In this case, for example, I was using a map to count all the possible points. But at the end, I mean, we have the board. The board is 81 or about 300 position at most. So instead of using a map of all the points, I just use an array of all the board and just put the value where I need. And this is a much more memory efficient structure, and this was a bigger improvement. But this is a kind of improvement that, yeah, it's mostly about the CPU. This is kind of, yeah, that's something that is quite easy. And okay, everything is clear up to now. I hope so. This is the main algorithm. Okay, so I explain you the rules. Let's say that we have the code that is able to move, but how we calculate the best move? The typical approach that chess kind of program uses is like having some kind of heuristics of shapes, which is better, which is worse, but are quite they are not really working very well with Go. But there is something new called Monte Carlo research, which, interestingly enough, I used to work at least in a bank, in finance, and also the financial derivatives product are tested with something called Monte Carlo research. I mean, with exactly the same algorithm to calculate the price for sophisticated derivatives. And the idea of a Monte Carlo research basically is we have a tree of all possible moves, which in Go will be too many to explore completely, like in chess. So we just take some rule at random, some moves at random. And then, so let's say they have this one, and then we decide which is more interesting from a point of view, where is more chance to have a winning position. And then we start here. We start a new node. And then from this node, we have this random, the board, and then we just start a random play. So basically, starting from this node, the computer play random moves, completely random. And then just to remember who win on these random moves. Being random moves, you can do very quickly because it's just random. It doesn't have any. The only check is that the move is valid, let's say, but there is no checking on the sophistication. And the point is that let's see. Okay, no. If general configuration is slightly more advantage for one of the player. Playing random moves, not just once, but just tens of thousands, hundreds of times of time, give statistically most chance to win to one of the player. So you just play random a lot of time, and if the position is better for one of the player, you get more chance for that player to win. So in this case, basically, you can use all your CPU to play these random moves, and then having some, you backpropagate who is winning, so you keep the winning percentage over the nodes. And you can keep going, and your results are better and better. But this also means that you have a kind of good result from the beginning. From like a few seconds, you are already able to have a kind of a decent move. And then if you run and run and run with more computer. If you are Google, you have 1,000 computers running in parallel. And then the first software, the Google AlphaGo was doing exactly this, with one more step that I haven't implemented yet, that instead of just choosing random move, which move to try, instead of being completely random, Google use AI, use deep learning to kind of, from this position, I would kind to try this, and this. It seems the most interesting move. And then on these moves, he started doing the Monte Carlo research. So it's a Monte Carlo research plus deep learning intuition, let's say. And this is definitely something that already now is beating any human. But this is how we implemented it in Kotlin. And you can see the code. I think it's quite easy. And so basically, this is the main. You select the most promising node. You simulate a random play. You get the winner, and then you propagate the result to the tree. One nice thing about Kotlin, there's something called tail recursion. Do you know about the tail recursion? So the idea is that if you have a recursion function in Java, and the recursion call itself, at some point you have a limited amount of the size for the stack. So it will go on Stack Overflow. But if you call the recursion is done in the last possible instruction, basically, what the compiler can do is say, this is the last possible instruction, so there is nothing after this. So I don't need to keep a stack element for this. So I can do the tail recursion, so I can do the recursion without allocating the stack. So that means that you can do this as many times as you want. You will never get out of the stack. It only works in Kotlin. There is a way, but it's very complicated. But this only works if your recursion is done at the last possible instruction in each. Will the
compiler complain if it's not the last possible?
Yeah, of course, you want to compile because in Kotlin you have to put this annotation tailrec to say try to use the recursion for this case, and if it's not possible, you won't compile. But it's not done automatically, so you need to specify. Which, by the way, is also something that they are looking to move in Java as well. But for the moment, you can. Yeah, and this is how you select the first node. Basically, you check if all the possible children of a node are visited, and if it's possible to have another move. And in that case, you select the node. Otherwise, you add a new random child. Okay. I think I missed. Okay. So next step is all we saw up to now. It was just a single thread. It was exploring the tree step. But how we do with many threads, which is quite tricky because let's go back a few slides. Yeah. If you are here and you start exploring, many threads are starting exploring different things. There is it's easy that you are exploring the same things twice, or when you're updating the result, you kind of mix the result. So it's not easy. One solution is having a kind of I mean, the exploring part is fine. The problem is when you backpropagation and when you select the next node. So one thing is that you can put a lock on selection and backpropagation. So those are locked. And instead using just the thread to do the simulation mostly. So to do the calculation. But it's not optimal. And you need you also have all these locks in your code. So another way is basically to use something also cool that Kotlin has and Java not, at least for the moment, which is called coroutines and channels. So basically the idea is that coroutines are kind of a lightweight thread that they talk each other, not using locks or shared memory, but using channel, which if you know Go as a language, also it has a channel. And the idea of channel is like a pipe, so you put something from a thread and you can read from the other thread. So in this case, I can use one coroutine. We'll just select and update the result. And then when you select a node, basically, then we have many other coroutines that just do the random play. So when we select a node, okay, this is node worth exploring. We send the node to one of this one. We don't care which one. And soon as one of these have a response, they give back the result, and we update the statistical, and we can select a new node. Now, the nice thing is that these coroutines are completely single-threaded in a way. So they don't. All the mechanism to select a node to update the statistical will always run in a single-thread mode. So I don't need any kind of synchronization, locks, or stuff like that. All this stuff, random play is also working, each one in a single thread mode. So the final code is much easier. You just get the result and then export it. Try to explode this node, try to explode this node, and then get the result back. Is it clear? Probably you want to see the code. And this is how the code looks like. So we have the channel. So basically the channel are two, one to send the node and one to get the response. And then we create as many workers as we want. For my PC that have 4 cores, I see that 6 workers is a kind of good number. Can be more. If it's less, it's not so good. If it's 6 or 8, it doesn't really change. If it's like 25, it spend more time trying to synchronize on all the coroutines rather than doing the work. So it's not as good. And so for each worker, you create the actor, which is kind of this idea of some class that stay in the coroutines and work locally. And then return the result, basically, just a pair. And then in the actual code, this is the setup, and this is the actual code. For each one, basically for each message that came, so consume the message that came in the channel, you get the message, which is this it, this one. This is kind of a lambda. And then you get the node, you play on the node, you get the winner for the node, and then you send the winner to the statistical update. And this is how the actor actually is done. But I wanted to show you, a bit more code. Okay, and these are the results basically. So from always on my laptop, single thread I have a more or less in 10 seconds I have a more or less 40 key, which is run. If I fake the rollout, so there is no rollout, I just fake. I have about 1 million. And which is kind of you know, to have a benchmark you need to know which is the time that just to set up your stuff. And if I do with the multi-thread with the logs, you can see I can mostly do double of a single thread, because logs, even if I have 4 core, I have only double the performance than a single thread. If I use something more smarter, so like the no-logs algorithm of a concurrent hash map, which use compare and swap instruction, which are faster than logs, I can do like about 2 times 4. But if I use channel, I can do almost 4 times. I can be almost perfectly multi-thread. And I can show you the code. It's really, I'm not making up numbers. Yeah. Sure?
When you use the coroutines and channels, what's the size of the thread pool you're actually using?
It's you can define, but the default is that your number of cores, which is actually number of logical cores in the computer. So hyper-thread cores, so for 4-core CPU will get 8, but you can change that, but it's quite a good default. And the idea that basically you can have as many coroutines you want, like you can have 100 million coroutines, no problem, but they will run on like 4 threads or 8 threads. I don't know if some of you went to the Russell talk yesterday about concurrency. No? Okay, but he was talking exactly about this kind of stuff. Channels are much better than logs to do concurrency. Okay, I want to talk about next step. Garbage collector is also incredibly important, and for this kind of high performance profiling. And also I have this experience in banking system that people tend to forget that we have a garbage collector that really matters a lot. And of course, if you are a very small program, website, stuff like that, you don't really feel. But if your system is under stress, if your CPU is closer to 100%, then garbage collector definitely matters. And I don't know if when you have a garbage collector, you have 2 parameters. One is you have 2 goals. One is throughput and one is latency. You know what is? Who know about the throughput? What the definition?
Operations per second.
Yeah, is basically how much work, useful work you do. And what is latency?
Like 39%.
Yeah, the latency basically is the longest or the number of polls that you have. So garbage collector they all work in a kind of way, so they know which, they try to identify which memory is not used, and then they throw it away, and they put again as usable for the rest of the system. And they all work like this. But the most efficient way to do this is stop everything, do the cleanup, compact, and then restart everything. This is the most efficient way to do it. No question asked. The problem is that in that period, when you clean up everything, your application is completely locked, is not responsive. Which, if you have a computer doing Go, is quite okay. I mean, yeah, 2 seconds is doing this calculation, is not responding. Nobody got hurt. I mean, if you are a very irresponsive website, it's not good. So modern GC, most of the science of the modern GC is about trying to reduce the latency. Still, if you have a kind of a batch job, like this kind of job, also in the banks, you have a lot of report job and stuff like that. It's already late. It's not, I mean, latency is not that important. The throughput is much more important. So here you can see the using my PC. This is the numbers that I have. And let's start from the fastest one, which is called parallel old garbage collector. And note that that old means that is paralleling the old memory. It's not an old garbage collector. It's not that there is a parallel new, a parallel old, but actually parallel old is better than parallel new. So just remember, not think about. And if you just need the throughput, this is definitely the better. There is no way that you can beat. Not even in the future, because I mean, unless they discover some bugs or some tricky part, there is no way that you can do better than stop the world and use all your core to clean up the memory. Then the second best is the concurrent mark and sweep, which was the default up to Java 7. It became available as an option in Java 8, but not more the default. And it will probably remove it to the next Java. So Java 11 will be probably the last Java with concurrent mark and sweep. And the reason they are going to remove it is because there are better one as latency. It won't be as good as parallel for throughput anyway. And it's very, very complicated. It's the most complicated of all them. So they said that this is no way that we can improve on this. It's too complicated. Let's do something simpler and better. Then the second one is the Shenandoah, which is a Red Hat garbage collector. It's not available in the normal Oracle OpenJDK, but you need the Red Hat JDK to use. Which is very modern. All the other, all these parts are very modern, and all these parts are slower, but they still have a much better latency. So the stops are very small. In the top one, basically, there is no stops. It will just use other threads to do the work, but the program have 0 stops. And the Shenandoah has these things called passive that basically force it to work in a kind of a high throughput way that is faster. Then GC is the current standard garbage collector for the default one. Shenandoah is the Red Hat, and the ZGC is the new one, which is still experimental in Java 11, and will be kind of probably will be the default in the future. But you needed to tweak a bit to have a kind of. But I really now to want to show some code. Any question? We have basically no time for the code. I'm sorry. Okay, this is the code. Well, let me first let's run the test just to. This code is on GitHub, so please feel free to try to run. So this is the computer playing against the computer, and it's defined at 10 seconds for move. So we'll try to play for 10 seconds and figure out which is the best move. It's random, so it's not given that if you replay, you have a different result, slightly different. Still, the moves are kind of good moves. I mean, moves that a human more or less can understand, and if you play against it, it's kind of 10 seconds, I can beat it. 30 seconds, I cannot probably beat it anymore. So you can see your level. And this is the number of rollout. Any question? I mean, I can.
What's the number next to runouts mean? The number of positions is checked.
It's the number of rollouts. So for each, how many times you try to run the wall till the end, basically.
Why does the number get bigger when you go down?
Yeah, because at the beginning is 0. It's for each move, basically. So that means that each second, how many rollouts did. So at the end of the 10 second is more like 150, more like, right? And you can see that, for example, here is trying to capture this one. And the white one, I don't know if it's white or black, instead of trying to protect this, decided to surround here, so this capture. So there is a kind of a logic. Yes. Any particular question? I mean, I can stop. For example, wait. So this is using the parallel hold, but if I say no, let's use the G1, which is it's the default, so I can just say don't use any particular things. By the way, this is something that you should always do. In your production code, I don't know if you read, put the garbage collector logs. Basically, running the garbage collector logs give you basically 0 overwork. I mean, there is no slowdown to activate the garbage collector logs. And they are very useful to diagnose in production. If you have especially if you have spikes of 100% CPU for a while, 9 times out of 10 is because of garbage collector. And it can be because, for example, in my code I have a bug, not exactly a bug, but basically I was creating more temporary objects than strictly necessary. And also because Java is not so smart on escape analysis. But so basically, just creating this object, then this object went directly to the garbage collector because it was out of scope very quickly. But just the number of objects was the allocation was 2 gigabytes per second, just for this object. It was slowing down the whole application, even if it was almost no CPU cycle. Just the number of allocation the memory was slowing down. Just switching this down had 0 impact in the single thread performance test, but in the actual game it was a big improvement, like a double. And you discover this kind of stuff using the the garbage collector logs. And this is the G1 in the meanwhile, and you can see that it's not that slower. It's not that slower. But there is a trick, and the trick is that Yeah. Where it is. Where is edit configuration? Yeah. That we give him 12 gigabytes of memory. And this is another thing of a modern garbage collector. This program doesn't take more than 1 gigabyte of memory. It can work with 1 gigabyte. But if you give much more memory, basically you keep allocating memory, and then the garbage collector can clean up the memory basically at its leisure. So the program is actually much faster than if it runs, if you just give let me try. I'm not sure if it works with 1, but definitely it works with 2. Now basically what's happened is that the garbage collector, it finished the memory very quickly, so I have to stop and clean up, and stop and clean up. And this should definitely show in the result. Well, not so much as I was expecting, to be honest. I'm not sure if it's actually working, but we can see. Well, we can also let it run, and then just last time before leaving you go. Where it is my slide. Because it's, I want to show you basically the I don't know. The garbage collector logs. Maybe how many of you have ever read the garbage collector log? Okay, I'm sure that it's really useful. It's really something that you should look at. And also, it doesn't matter which language you're using in JVM. And these are the logs. You see, this is the current one, and then it also does the rotation for free. And this is, you can see that at the beginning it says that it's using G1, and this is the size. So if you are unsure if it's actually using the size, you can check. And then there is a lot of information if you know what to looking for. And you can see that, for example, here it's taking 13 milliseconds to do the cleanup for the next mark. Because G1 basically works that instead of cleaning all the memory all the time, it just try to clean up a bit of memory and then do a bit of time. So basically, using this generation. And then the whole cycle is almost taking 1 second. But it's not stopping the world, because while it's doing, your application is keeping running. So you don't feel a stop a world like in parallel hold. Okay. Question or tweet me, ask me anything. I think I have to leave you go now.